Good afternoon, everybody. On behalf of Group 3, consisting of myself, Will Lindquist, James Ergel, and Paige Gore, this is our presentation on the System ID Lab. Burdell Inc. has been tasked with creating a controller for a DC motor made by Quanzer Inc. The motor is to be used in a robotic arm in an automotive manufacturing plant to allow for position control. The problem statement for this lab is to determine which control model will best represent the DC motor response. Case 2, which has a voltage of 2.3 volts and a frequency of 0.1 Hz, or Case 2, which has a voltage of 3.5 volts and a frequency of 15 Hz. To begin this lab, the accuracy of the motor system will be evaluated based on the motor response at varying input voltages. After optimal operating conditions are determined, either Case 1 or Case 2 will be chosen. This lab consists of a MyRio activated DC motor system shown in the figure below. The MyRio reads LabVIEW functions with voltages as their input. The data collection plan for this lab is broken up into 3 parts. Part 1 is the system nonlinearity, Part 2 is the time domain system identification, and Part 3 is the frequency domain identification. The figure to the right shows the data collected in Part 1 of this lab. Those points circled in red are in the safe operating region of the system and fall within the dead zone and the saturation limit. The dead zone was found to be at approximately 0.015 volts, which is at the bottom left, and the dead zone is where the input voltage is unable to overcome the inertia of the system. The saturation limit is determined to be approximately 7 volts. This is the point in which the motor approaches the upper speed limit capable of the system, so increasing the voltage past this point has little to no effect on the rotational speed of the flywheel. A linear regression was performed on the linear region of the data collected for Part 1 and is shown in the figure. The slope of the regression line, which is the motor gain, was found to be 9.0466. The time motor constant was found by taking the average of the time values for the linear region. The time motor constant value was determined to be 0.1010 seconds. And note that this time motor constant is not dependent on voltage.
This experimental plot shows the step response in the time domain for all Vn values in the linear range of the data. Km increases slightly throughout the linear range. Tm has minor fluctuations throughout the range but remains fairly constant. This reveals that the model is not 100% precise. Uncertainty within the measuring devices could be a contributing factor for the varying Km and Tm values. Another factor could be the response of the motor varying due to imperfections in the components relative to the ideal motor design. To find the composite values of Km and Tm for the time domain model, one can use the equation shown here. When you zoom in on the experimental steady-state response, the data shows slight sinusoidal variations around the steady-state value. This is most likely due to the control system not being able to perfectly maintain the expected input voltage, but slightly overshooting and undershooting as it adjusts to maintain the desired voltage. Here you can see the theoretical step response plot. This plot does not have the same variations at the steady-state rotational velocity that the experimental plot had. This makes sense because the theoretical calculation assumes a perfectly constant input voltage. The Km value remains roughly constant when mass is added or removed to the system, which is what was expected. Km depends on steady-state speed and voltage input and is time independent. Because the added mass reaches approximately the same steady-state rotational speed, the Km value should be roughly equal. The Tm value increases, which is to be expected. Tm is dependent on steady-state speed, time, and Km, but is independent of voltage. Increasing the mass within the system increases the inertia of the system, which means the same power input requires much more time to reach the steady-state rotational velocity.
On this slide, you can see the Bode plot of the experimental sine wave data. The data follows the expected trend with the constant magnitude approaching the cutoff frequency and the phase lag increasing through the cutoff frequency. The two plots generate different cutoff frequencies, which are reflected in the motor constants below. On the left are the constants using the cutoff frequency within the magnitude plot, and on the right are the constants using the frequency from the phase lag. Both of these are different from what is expected from the time domain data, which is possibly due to the effects of inertia on the acceleration of the wheel due to the varying sine wave input, instead of the constant input used originally. On this slide are the Bode plots of a first and second order transfer function using the motor constants obtained from the magnitude plot. Based on the relative agreement between the time domain constants and the frequency domain constants, and the agreement between the first order Bode plot and the Bode plot from the experimental data, the first order system appears to be valid for an approximation. On this slide are the key results from our experimentation. The usable range of the system is from approximately 15 millivolts to approximately 7 volts. While both cases operate within the usable voltage range of the system at 2.3 volts and 3.5 volts respectively, case 2 operates above the cutoff frequency at 15 Hz, which means some of the signal will be reflected or attenuated by the system. Therefore, case 1 at 0.1 Hz and 2.3 volts is preferred.
Thank you for listening. Any questions?